0. Ignition. And liftoff.
Svemirski centar John Fitzgerald Kennedy glavni je NASA-in lansirni centar za misije s ljudskom posadom. Iz ovog kompleksa lansirani su svemirska postaja Skylab i raketoplani iz programa Space Shuttle. Smješten je na istočnoj obali Floride, uz vojnu bazu Cape Canaveral. Te dvije organizacije blisko surađuju i zajednički upravljaju nekim objektima. Centar Kennedy ustoje i baza za lansiranje robota, komercijalne letove u svemir, istraživanje metoda uzgoja hrane te vađenje resursa izvan našeg planeta i njihova iskorištavanja na licu mjesta. Na površini od 58.000 hektara smješteno je 700-tinjak objekata. Među njima je i 160 metara visoka montažna hala u kojoj se sastavljaju najveće NASA-ine rakete. Kompleks obuhvaća kontrolni centar, pogon za testiranje, spavaonicu i prostorije u kojima astronauti borave uoči leta u svemir, tvornicu raketa i modula te sletnu pistu dugu 5 km. Tu je i centar za posjetitelje, otvoren za javnost.
I've been working at NASA's Kennedy Space Center for 16 years. I went from undergraduate at the University of Miami to graduate school at Georgia Tech. And there I started working a little bit into the space application, but I really wanted to work in environmental chemistry, and I came down to Kennedy Space Center to work on environmental chemistry.
I've actually been at NASA for just about 2 years, so I'm fairly fresh here, but I interned for 2 years prior to that as well. I started kind of growing my interest in space because that idea of using space exploration as an approach to understand what it is to be human was really what got me involved here.
I'm a plant scientist at Kennedy Space Center. I've wanted to do this job since I was 12 years old. When I was in 7th grade, I had an agriculture teacher who was invited here to Kennedy Space Center to learn about the research going on in space agriculture, and I thought it was the most fascinating thing ever.
I've been at NASA for about 14 years. I knew I wanted to do this in middle school. My brother was ahead of me. He went to high school and was getting involved with the first robotics competition. Then NASA started landing these rovers on Mars, and I knew that's what I wanted to go do. I wanted to build robots to fly in space.
Istraživanje svemira vrlo je uzbudljivo. Kao u svim NASA-inim centrima, stručni timovi u centru Kennedy spremni su za akciju.
So I've always liked plants. I grew up in a family with a grandmother and a mother who are avid gardeners. So that really helped me to build this connection with agriculture, with figuring out where our food comes from, how we get that food to people, seeing how we can apply this agriculture to space. It's such a unique environment. We have very different challenges than terrestrial agriculture has. Learning about the challenges for space and for space agriculture, and then figuring out how to apply them both in the space environment and also on Earth. It's really at the juncture of many different fields. It's plant science, it's chemistry, it's microbiology, agriculture and engineering, and you get to do all of these different things and interact with all of these wonderful people, and that makes it really important and fun to study.
I came here to work on environmental chemistry, but I was able to take that technology that I was working on and morph that into something that I could use for exploration of looking for ice in the lunar South Pole.
NASA was landing robots on the surface of Mars, and seeing that while I was taking classes was very inspiring and motivational to get my degree so I could get involved and help out with that. And so I feel very fortunate to be able to have this job doing exactly what I've always wanted to do, building robots to explore our solar system.
Since we've begun exploring in low Earth orbit and during the Apollo era at the moon, the trash and really the logistics discussion was an afterthought. It was something that needed to be taken care of quickly because it couldn't be something that we needed to spend a substantial amount of our efforts doing. Now as we venture out further away from low Earth orbit into deeper space, we now are seeing that logistics management and trash management is beginning to be a problem. Now we are accruing significant trash on the habitat, which can have problems with performing orbital maneuvers when we're trying to propel ourselves to Mars or somewhere similar. It also has a problem with volume on the spacecraft, because now it's taking over the habitable volume that the crew should be able to live in and sustain themselves in. Those are the immediate problems, and why now we're revisiting trash management for longer duration missions. But there's also the second and more beneficial aspect of it in terms of extracting the resources that we can get from the trash material. And as we venture out, being more sustainable and reusable and repurposing as much as we possibly can is a focus that we have going forward.
NASA stalno konstruira nove tipove svemirskih robota za istraživanje i iskapanje.
RASER is a robotic excavator. It stands for Regolith Advanced Surface Systems Operations Robot. And this is a brand new excavation technology because we need to do excavation, we need to do digging on the surface of the moon so that we can capture some of the resources that we have on the moon and be less reliant on shipping everything that we need for our missions from Earth. The RASER is going to be able to make us sustainable, have longer-term missions on the moon, and really enable a human presence on the surface of Mars. RASER is a brand new excavation technology. We can't excavate on the moon the same way we excavate here on Earth. On Earth, we have really large, massive vehicles that we just put more steel on to make them heavier, and that gives them the power and the energy, the reaction force that they need to dig. So when they interact with the ground is what gives way. We can't afford to launch vehicles like that on rockets. It's just very inefficient, very costly. So we had to develop a new method of doing excavation where we can launch it on a rocket and land it on a planetary body that has less gravity than we have here on Earth. That's what RASER is designed for.
CLPS is the Commercial Lunar Payload Services. We're going to be launching 4 spectrometers on these CLPS missions. And a spectrometer actually measures the different gases that are going to be around the lander and in different samples that we're going to analyze. So all of the 4 different missions are going to look at slightly different aspects of exploring the lunar surface. A mass spectrometer is used to analyze different gases. It works by ionizing gases and then separating them into a mass separator or a mass filter. And what we're going to learn is different aspects of what's around the lander. When the CLPS landers go to the lunar surface, we need to understand what kind of environment we're creating on that lunar surface. That gives us a background of kind of what we expect to see when we're on the lunar surface. Then as we go towards more exploration-focused goals, we're going to actually be looking at resources on the lunar surface.
Early on in my life, I had the luxury of having a pilot for a dad. Having that opportunity to travel the world was very within my accessible wheelhouse. Seeing the world and getting this global perspective very easily allowed me to understand the problems that we have with trash management here on Earth, not only in America, but all around the world in terms of not really reutilizing our trash items as best we possibly can. The problem on Earth is clear, and now that we have a space application in mind, we hope that sustainable trash processing in space can act as a perfect example for sustainable living here in America and around the world. The approach that we're taking here at the Kennedy Space Center is a term that we've coined trash to gas. This essentially means that we are collecting all the astronaut crew items and using a thermal degradation process, most notably combustion or steam reforming, to gasify the astronaut crew items into products that can either be reutilized on board or vented overboard for mass and volume reduction purposes. So the state-of-the-art system is a system that we call OSCAR, the Orbital Syngas Commodity Augmentation Reactor. And OSCAR, we got the term from Sesame Street. It essentially is a subscale design that we've been able to test in suborbital space to essentially demonstrate how feasible trash gas operations are in the microgravity environment.
NASA-ini roveri autonomna su motorna vozila koja putuju u svemir, te obilaze površinu Mjeseca i Marsa. Istražuju velika područja, uzimaju uzorke tla i donose ih na Zemlju.
So RASER is still in development. We've built 2 generations of this prototype robot. We've been testing it in a lab. We have facilities here at Kennedy Space Center where we can drive the robot in simulated lunar regolith, lunar dirt, and test how well it excavates, how well it drives. So currently we're developing a new version of Razor that we're going to fly to the moon on commercial landers that we call CLPS, Commercial Lunar Payload Services. And these are commercial landers that NASA is partnering with to fly some of our technology so we can demonstrate it on the surface of the moon. We're going to demonstrate Razor on the surface of the moon. It's important that we fly a demo mission where we can prove out this excavation technology in a lunar environment because we've never done anything like this before. We've flown a lot of robots to Mars, but we've always called those robotic scientists. They're like geologists on wheels, right? They have all these delicate science instruments. They move slowly. They're very precise about the work that they do. Razor is a robotic construction worker, right? This has to do one very specific task, and it has to do it over and over again. And it has to be very robust so that it can survive the amount of operational time that we require. Pulling the resources out of the moon dirt takes a lot of time, takes a lot of regolith, a lot of dirt to do that. And so we're going to demonstrate that we can excavate up to 10 tons of regolith on the surface of the moon. Right now, we've only excavated a couple kilograms. We're talking about 10,000 kilograms. We're also going to drive a lot further than we've ever driven before on another planet. Right now, the record is set by the Opportunity rover from Mars, about 46 kilometers. Razor is going to drive thousands of kilometers. One of the challenges you have with an excavation robot like this is making sure it's robust. You're putting so much time on a robot like this, and you're doing it in a really, really harsh environment of the moon. Vacuum, huge temperature swings from cold to hot, a really abrasive lunar material, regolith, that wants to eat away at the metals and materials on the robot. How do you design a robot to work in that harsh environment for such a long period of time?
As we think of the challenges of human space exploration, one of the biggest is actually how to sustain the crew on these longer duration missions away from Earth. And food is obviously one of our most important inputs on Earth, and it's going to be one of the most important things for the astronauts as they're living and working away from space. Figuring out how to effectively feed the crew to ensure their food security, their health and performance, good diet, foods that they like, and foods that will maintain them over time is a real challenge. Our packaged food system is excellent, but those packaged foods actually degrade over time, and the quality and the vitamins within them break down. So we're looking at growing crops in the near term to supplement that packaged diet and to help ensure that we can provide all of the nutrients for the astronauts and also to provide variety. And then there's the psychological aspects of having this little piece of green growing earth with the astronauts when they're, far away living in this extreme stressful environment. And then in the longer term, if we ever want to live off Earth for longer durations, food is really heavy, it takes up a lot of space, but seeds are light. And so we want to be able to grow as much of the food as we can, in situ, rather than transporting it all from Earth. Food is really key to us being able to live off Earth for long periods of time, and plants are one of the ways that we can get there.
Misija Prime 1 spustit će bušilicu iz spektrometar Masa na južni pol mjeseca. Cilj je ispitati mogućnosti iskorištavanja resursa na licu mjesta. Lansiranje misije predviđeno je za prosinac 2022. raketom Falcon 9.
We're going to be sending the first in-situ resource utilization instrument to the lunar surface. And so this is the mission called Prime 1. And what Prime 1 is going to do is it's going to pair a mass spectrometer, which is the M-SOLO instrument, with the Trident drill. And we're going to actually drill samples from up to 3 feet below the lunar surface, bring it up to the surface and look at what volatiles or what resources are there. So the main resource we're interested in is water, but we're also looking at other volatiles and other resources that are there. And so it's important to really understand that whole picture of what is at that lunar surface that we can use them as resources to enable future sustainable exploration. And this is a really exciting program for us. This is Kennedy's opportunity to launch 4 instruments on different CLPS missions.
So Razor is an autonomous robot. It's actually what we call supervised autonomous. This means that we're going to have ground controllers here on Earth monitoring the operations of Razor. At a ground station, we will upload certain positions that we want the robot to go to, and it'll be up to the robot to complete those traverses on its own. We're going to give it high-level commands like move to the excavation zone and begin digging, all the while monitoring its progress and waiting for reports back on if it reaches some anomalous condition, it reaches an obstacle and needs advice from the ground controllers about what to do next. Razor drives autonomously. We're going to use navigation aids for this particular mission. Our real focus is putting a lot of time on excavation. We want to move a lot of dirt, essentially. We'll use a lander as a feature so we can use it as a navigation aid. Razor will drive around the lander, it will find an excavation zone, and it will begin to collect regolith, fill up its drums, drive the regolith back to a lander, and only report back when necessary. Anywhere you go on the moon, if you reach down and grab a handful of dirt, 40% of what you hold in your hand is oxygen. And oxygen makes up 80% of rocket propellant. So that means anywhere we go on the moon, if we were able to dig up that material and pull the oxygen out of it, we can refuel our rockets and we can go further. We can go to Mars. We can expand our reach into the solar system and do more exploration.
We need to understand the resources there, and we're looking at the gases that are going to come off from that lunar regolith. What we're doing is really quantifying how easily that resource is extracted and how deep that resource is. So you can imagine that if you're going to find a resource that's just under the surface, it's much different than if you're going to find a resource that's, say, a meter or 3 feet underneath the surface. And so we need to understand what those gases are and how deep they are found. We need to understand how deep those molecules are and how easily they come off the lunar regolith, because that'll help us design the tools we need to extract those resources so that we can use them in our Artemis exploration program.
Kako bi ljudi mogli dulje opstati u svemiru, NASA mora ovladati tehnologijom uzgoja biljaka u uvjetima koji ondje vladaju.
We're doing a lot of testing here at Kennedy Space Center to understand how plants grow in space-like environments on the ground, so conditions of temperature, humidity, carbon dioxide that would be on a spacecraft. At the same time, we're doing experiments on the International Space Station. We have crop growth systems that are growing, plants on the International Space Station. So we can compare between flight and ground how the plants grow in the different environments. For the Moon and Mars, we have some gravity, not as much as we have here on Earth, but we think it may be pretty similar to the systems that we are growing here on Earth in our chambers. And then for transit mission, say to Mars, we think that will be pretty similar to the International Space Station. Some conditions may be different, things like space radiation. So we actually have a facility that can simulate a space radiation beam, and we can test plants or seeds in that environment. We have researchers doing research to simulate that space radiation effect on the plants. We try to figure out what impacts gravity will have, what impacts radiation will have, and what impacts these other environmental factors that plants respond to, such as temperature, light, nutrients, atmosphere, etc., will have, and mimic those as best we can. We're going to have to try things in real locations, so we're very much looking forward to being able to test plants on the Moon as a great way to test how plants will grow on Mars, because the Moon and Mars have a lot of similarities in those respects, partial gravity and space radiation.
The Oscar project itself started back in 2017. This has really culminated in 2 successful suborbital demonstrations. So we performed suborbital flight demonstrations with Blue Origin and their New Shepard vehicle, essentially getting 3 minutes of microgravity to test the design and test the processes that deal with trash and gas operations in the microgravity environment. And then we use those as a stepping stone and take those lessons and learn from them so that we can use all the information and data from these suborbital flight campaigns and use them for the next generation trash and gas process, where we'll be designing a full-scale system to operate for a crew of 4 for the next generation of human spaceflight.
Pri projektiranju strojeva prilagođenih za rad u svemiru treba predvidjeti razlike u okolišu.
So the way Razor operates is a lot different than excavators on Earth. We have unique digging tools that we call bucket drums. They're on either end of the robot, and these are hollow drums that have small scoops that are staggered around the outside. And when we want to excavate the regolith, we lower these bucket drums down to the ground, and we start shaving the surface of the regolith as we drive across it. So the bucket drums themselves are a unique digging tool. They have these scoops that are staggered around the surface of the drum. And these small scoops help to reduce the forces that it takes to dig into the dirt. Instead of having one large bucket or one large blade that we dig with at a single time, these small scoops, they average that excavation force as you dig. And so that helps us reduce the reaction, reduce the forces that the excavator sees compared to traditional excavators. So we take our excavation tools, these bucket drums, and we put them on either end of the robot. And they dig at the same time, but in opposing directions. And what this allows us to do is react the excavation forces on the bucket drums off of one another at the same time. So you're no longer relying on the weight of the excavator to give you traction to react to your excavation forces. You react those forces in the bucket drums themselves. This allows us to do excavation with a really low mass robot on a low gravity body like the Moon and Mars. The bucket drums on Razor not only act as our excavation tools, but they allow us to store and transport the regolith. So they're hollow, and as we rotate the drums through the regolith, the dirt moves to the center of the drums and gets kind of trapped inside. We can haul that regolith to wherever we want to deliver it, and we reverse the rotation of the drums, and the regolith comes out the same scoops that it entered in. So this is, again, a very efficient way to not only excavate, but haul and deliver the regolith all in one vehicle.
We are really excited to send this modified commercial off-the-shelf instrument to the surface of the moon. And we are partnering with Inficon, who's a company in Syracuse, New York, and they build mass spectrometers that are typically used here on Earth in the semiconductor industry. We're building on what they have done with their instrument development to really take what they've done and bring that technology to the lunar surface. We have our expertise coming in to make modifications for spaceflight. We look at vibration, EMI, and we modify the instrument a little bit, and then we are able to take this commercial instrument and fly it to the moon. We're taking instruments that they are building and sending them to the moon. And it's something that they get all excited about, you know, seeing their instruments that are typically used in industry that are now going to go and land on the moon.
Razor's also designed to be really robust. You'll notice that there's not as many sensors, there's not as many motions and actuators on this robot. We're really trying to focus on a very simple, very robust vehicle because it has to operate for so long in such harsh conditions. We want to make it as hardy and robust as we possibly can. We minimize the number of sensors that we use. We have different techniques of how we do our autonomy so that we don't rely on very sensitive tools and sensors. It's mostly cameras, onboard sensors that provide that autonomous navigation. Razor also has some unique mobility capabilities. The bucket drums can act as another set of wheels if we were to get in some scenarios where the mobility system would be stuck. So we've seen this before with robots on Mars, where you drive through unknown soil and it's very softer than we expect, and the robot can spin its wheels and get stuck. Razor can put the bucket drums down and essentially have another 4 set of wheels on the ground, and we can get out of scenarios like that. We're also able to flip ourselves over. If we were to be digging deep trenches, for example, or building a tall berm, and the robot were to take a tumble, that would be mission over for most space robots. But Razor can recover from scenarios like that, and that's all part of the design philosophy, trying to design something to be robust. If we were to have an anomaly on a mission, it's not the end of the mission. We can recover from it and keep going.
Kako bi svemirska putovanja bila što kvalitetnija i uspješnija, u NASA rade na razvoju održivih procesa.
Here at NASA, we really are focusing on, for this next generation of spaceflight, using ISRU, or in situ resource utilization. And this means that we're being sustainable, but true sustainability is the approach of utilizing everything that we bring with us. And that's the beauty of a trash of gas and of the Oscar subscale design, is that we're really trying to promote true sustainability within spaceflight. And that will in turn reap benefits here on Earth as we create technologies that make it truly sustainable as we go onward. We gather up all of the various astronaut crew items. This comes in, we're including metabolics, inorganics, biological waste streams, everything other than metals that can be a waste item on the habitat will be processed through the trash of gas system. So they are collected, injected into a combustion reactor where 100% oxygen environment and heat thermally degrade the trash items into mainly carbon dioxide and water vapor. So this is what's really important about it. Not only are you reducing the mass and volume via combustion, but you're also gathering water vapor and CO2, and the carbon dioxide can also be repurposed in itself to produce water and methane. So all of these products can be reutilized on board, or if they need to be vented, they can be vented. So after the combustion process is over, we flow the gaseous products through a heat exchanger where the condensables are collected and then filtered, and the gases are collected in 3 subsequent tanks to analyze them via gas chromatography and gas chromatography mass spectrometry. And these are really used to characterize and understand what other gaseous products other than carbon dioxide are present in our stream, so that we can either mitigate any concerns with volatile organic compounds, because they may be hazardous at high concentrations, or we can reutilize the other compounds that may be present as well. Anything that I can do, anything that I can touch to help sustain the human presence in space will in turn, I hope, let us learn a little bit more about what it is to be human itself.
Plants are really unique in the way that they respond to their environment. They are autotrophs, which means they use light energy to generate their own food, essentially. Through this process, they take up carbon dioxide and they fix that carbon into carbohydrates. You know, that's what makes the plant themselves, is this fixed carbon. And through that process called photosynthesis, they will generate oxygen. So in a lot of ways, there are perfect symbionts because, you know, we give off carbon dioxide, they need carbon dioxide, we need oxygen, and they give off oxygen. So plants are going to be an integral part of, I think, a future life support system. They can generate the atmosphere for the crew. It takes a fair number of plants per person to generate enough oxygen. But as we go farther and stay longer and scale up our crop growth facilities, we'll be able to start to do that, to help recycle the atmosphere. They're not only making food, they're not only having a psychological benefit for the crew, which we're starting to collect more data on, but they're also helping to recycle the atmosphere. So I think they're going to be really important in any future spaceflight environment. We're still collecting a lot of data on different crops in the space environment, but we've seen that, you know, plants that are grown in microgravity on the space station are equally as nutritious as their counterparts on Earth. They may have a more varied microbiological community because it's associated with that microbiome of the space station, so it might be different than what we see on Earth, but they're still safe for the crew to eat. We are collecting more data on what plants we can grow in those environments and how plants may vary. But so far we've not seen any showstoppers, so we think it's very feasible to grow crops for the astronauts to support them. We're growing more larger plants, so chili peppers are growing on the space station. We've grown a lot of leafy greens. We hope to grow tomatoes in the near future. We're adding to the candidate crop sweep, and we're also collecting human data. And we're getting feedback from the astronauts that shows that, you know, having the plants really seems to benefit them, their connection to Earth and their well-being, and a positive benefit to their food. They seem to really enjoy eating the plants when they have that opportunity. So all of the data are telling a really positive story for plants in space.
NASA surađuje s nekoliko partnera kako bi ispunila još jednu misiju. Upotrijebit će maseni spektrometar u svemiru.
For our missions, we are going to operate them real time. So we'll be getting data back in a live stream. We might have a little bit of a delay, but for the most part, we are looking at data, analyzing it, and making informed decisions about how we're going to do our science on the moon real time. And that's really exciting. For the Prime 1 mission, we are going to be on a static lander with our Trident drill, and we're going to be looking at the volatiles that are coming off from the surface of the regolith as they bring those regolith samples up from the surface. So in addition to Prime 1, our last mission for M-Solo right now is the Viper mission, and that pairs both the Trident drill and M-Solo from Prime with other instruments such as the near-infrared volatile spectrometer system, the NIRVIS system, and a neutron spectrometer, NSS, both developed out of Ames Research Center. And they're all going on a rover that's going to be operated for science exploration of the lunar South Pole. And so from there, our science is actually going to guide us, and we're going to be able to rework the traverse and replan where we decide to go based on the science that we're getting back real time. And so that's an exciting opportunity to really get science real time, analyze it, and then make informed decisions about where we want to go next, exploring that south pole of the lunar surface.
So this is really just the tip of the iceberg for robotic construction vehicles. This is the first robot of its type that NASA's ever attempted, but there's going to be a lot more that follow. We are demonstrating moving a significant amount of regolith, 10 metric tons, but this is only enough really to fuel one rocket, one ascent stage of a lander, so you get back into orbit. The future of this is moving to a sustainable architecture where we have several vehicles of different types to do not only excavation, but construction activities. Again, we want to use the resources that we find on the moon, the resources that we find on Mars, to start to build habitats that are sustainable. So this means propellant, this means structures, landing pads, and if we can use materials that we source locally, then that reduces our reliance on those supplies being shipped from Earth. We're going to start seeing larger excavators, more excavators operating in swarms and working together. We're going to see construction robotic vehicles that can build things like landing pads. We designed Razor to be very mass efficient and energy efficient so that we could launch it on a rocket and we could operate it in a low gravity environment. But what that also means is that we can move a whole lot of dirt with a vehicle that's really small and really lightweight and doesn't use a whole lot of energy. And so I can see applications here on Earth where we have excavators that are much smaller and don't require as much fuel to do the jobs that they need to do. So this could be about using energy efficiently here on Earth. This could be about autonomous technologies so that we can enable some of our terrestrial excavation and construction vehicles to do their jobs autonomously as well.
There are definitely some challenges when we look at modifying a commercial instrument. First really big challenge is really making sure that we make informed decisions about what we can use for our electronics. And so typically when we operate things here on Earth, we need to go with the fastest, best, latest processor, but that doesn't really work well in spaceflight because those chips and all of that high technology doesn't tend to last very long in a radiation environment. And so we really need to understand what kind of changes we can make to the electronics to make our instrument able to function in a different environment. It's important for us to really work closely with the vendor because we need to make sure that if we change out components, we're not going to change the functionality of the instrument. The chief scientist is actually our co-investigator for the instrument, and so we make sure that they are closely involved, they understand the changes that we want to make, and that we test with them. That's how we overcome that biggest challenge of making these slight modifications for spaceflight.
Istraživanje će im omogućiti da unaprijede proces uzgoja biljaka u svemiru.
The brick or biological research in canisters experiments were the smaller experiments where we can look at early seed germination and other biological organisms, so not just plants. So that's just one type of the hardware that we have available for research on the International Space Station. We also have our veggie chamber, which is more of our astronaut garden, kind of a larger plant growth chamber. And then we have our advanced plant habitat, which is really a plant physiology research chamber. The other hardware that we have there, a relatively new piece of hardware, is called Spectrum, which is a multispectral fluorescence imager for the International Space Station for plants and small biology. So with this suite of instrumentation, we can study a range of different organisms and look at them at very different environmental conditions to really disentangle the impacts of spaceflight and microgravity on the biology itself and try to understand how that's impacting, the growth and the genetics and other components.
The way that we develop technology at NASA, it's like a stepping stone or a ladder you can think of. We built and confirmed the feasibility of a subscale design, and the next step is to build a fully scaled design that is operable on the International Space Station so that we can prove the feasibility at a longer duration for an increased feedstock of trash. So this is going to be designed for a crew of 4 because the next generation of space flight is including crews of 4 as we venture back to the moon. And then once we confirm feasibility and operability of this full-scale crew of 4 system, Then it begins to scale up as our missions increase in crew size. So as we begin to learn more about how we can sustain ourselves on the moon, that means we can increase the crew duration size and the duration of the mission to the moon and onwards to Mars. So as the mission needs increase with the crew size and duration time, then so does the trash management system. The sustainable approach is to learn for a full-scale system for a crew of 4, and then it gets larger as our abilities and our capabilities improve with time.
Our goal is always to push technology to that next level. One of the things we're looking at is how can we take what we have right now, this instrument, and adapt it and push it even further. We see these different applications, not only for exploration, but for crew habitat. We need a ruggedized mass spectrometer. The smaller, the better. And so that's where we're going to go with this. And now that we've got a partnership, with Infocon, we can take some of their other designs where they're also looking at pushing the size factor and making instruments smaller and more compact, and taking that and modifying it again for space flight. And so we are looking at making these things more accessible to everyday scientists. And what that's going to do is it's really going to open up that opportunity for us to further all the science that we can do on the ISS and on the future of the lunar exploration in the South Pole.
Space crop production will be implemented in stages. Right now we're focusing on pick and eat crops, things that you can eat fresh without processing. So your salad crops, lettuce, tomatoes, peppers, maybe things like strawberries in the future. Radishes have been grown recently. Herbs, I think, are something that we'll start adding because those are things that you can add to the packaged diet. The longer we stay in an off-Earth location, the more types of crops that we can add, and then we can grow some things like sweet potatoes or potatoes, starting to kind of meet the needs of the calories of the crew and starting to supplement some of those calories. We'll need cooking equipment. You're not eating your potatoes raw, so we'll need at least an oven or a microwave or a way to cook those. But those are what we consider our intermediate crops. Then we have our longer duration staple crops, things like wheat and soybean and peanut. But some of those require even more processing equipment. So you have to have your milling equipment, and threshing equipment, and things like bread machines and tofu presses. And that takes more equipment, so more things launched from Earth. But it also will take either more labor or more automation. Once crop growth scales up, we're going to have a lot of automation and robotics to do the crop tending, because we're not sending astronauts to Mars to be subsistence farmers. We're sending them to explore Mars and to find out all of the amazing things about that planet.
Vidi se da stručnjaci iz centra Kennedy uživaju raditi na tim uzbudljivim misijama.
What I love about NASA is working on a project that was just an idea in my head. A group of team members getting together, coming up with an idea of how to solve this problem. How do we do excavation on a planetary body that has low gravity, and we have to launch it on a rocket. We can't have a bunch of weight. How do we do excavation? Trying to solve this problem, getting to take that idea, go fight for funding, get the funding, develop the technology, sitting in front of a computer doing CAD work, building the thing, assembling it, bringing it out to a rock yard like this and doing testing on it. The whole life cycle of the project, that's exciting to me, seeing something that was just a concept in your head, bringing it all the way to flight and actually launching it on a rocket, landing it on the moon, and seeing it operate. I mean, it doesn't get more exciting than that. I love that I get to come and play with robots at work.
I love NASA and I love working at NASA because it's a place where people can dream and turn those dreams into reality. It's amazing to work with people who have a similar passion, to me, and we all want to achieve incredible things for humanity. And I think being a part of that, I'm just really humbled to be able to be a part of this awesome team.
So I think the thing I love most about NASA is the freedom that we have to really push technology and go explore the areas that we see that need to be explored. When I started, we thought the moon was a fairly dry place. So that change and that push towards understanding that there's ice on the moon and that it's a resource that is something that we've pushed towards, and now using it as a resource, that ability to really follow that science and really push that technology is really exciting in terms of, being able to work for a place that allows you to do that and allows you to really go explore where we need to go explore.
It's just been an honor, really an honor, to be here at the beginning-ish of my career, make an impact with my time and with my work, to do something substantial, not just for spaceflight, but for all of mankind. I've been given the opportunity to make a sustainable trash management approach. That is my striving and my path to helping promote human exploration and onwards to the moon and Mars and beyond from that, so to truly be sustainable. That's really the approach here, and the benefit is a gateway to true sustainability.
Trudom koji ulaže u istraživanje svemira i eksperimentiranje, Svemirski centar Kennedy, glavna baza za lansiranje misija s ljudskom posadom, uvelike pridonosi razvoju cijele organizacije i napretku čovječanstva. To je jedan od najistaknutijih NASA-inih centara, koji obuhvaća i objekte otvorene za javnost. Jasno je da ljudi koji ovdje rade strastveno vole svoj posao.